Hi, Paige. It's me. How are you? Happy Tuesday. Hope your exam today went well. I'm sure it did. Listen, here are your questions right here. This one, the cylinder can in a sphere. And I actually didn't paste your drawing, but you were close. So this one's a hard one. The dimensions of a circular cylinder of max volume that can be inscribed in a sphere of radius r, where r is a constant, okay? So I'm putting the sphere in here, and we know that the radius of the sphere is some constant r, okay? And you know that the equation, circular cylinder of max volume, so the volume of a cylinder is pi r squared h, right? And what this question is asking us to do is to figure out what is the radius and the height of a cylinder of max volume, right? So this is what we're optimizing right here. But we have to somehow incorporate the constraints. And actually, if you look at this here for a second, we have a way of doing that. So this distance I just dotted, this red distance, do you see how this is exactly half of h, right? Okay. But you also see how, and I'll call this distance here c, okay? You see how r squared plus c squared equals capital R squared. You have to keep in mind here that r is a constant. So what I want to do here is incorporate this constraint, because r is the radius of this sphere, right? I mean, if you drew different cylinders in here, let me try and do one, right? If you did a cylinder looked like this, right, it's still a circular cylinder. The distinguishing criteria among all these different cylinders is that there's this constant r, which is the radius of the sphere, okay? So this is the constraint, r squared plus c squared equals capital R squared. I'm making a note to self that 2c equals h, right? Okay, so what I'm going to do here is I'm going to solve this equation for r squared and then put it into v. So r squared here equals capital R squared minus c squared. I'm going to go put this now into the equation to be optimized, and I get v equals pi. Here's my r squared, right? Capital R squared minus c squared times h. And now I'm very happy. I'm going to optimize, take the derivative. However, you'll notice here that I have two independent variables. Capital R is not an independent variable because it is a constant. And one could look at this and say, oh no, I have C and H. I wish I only had one independent variable. Well, but don't forget, C is just half of H, right? So C is just H over 2. So I'm going to do this. V equals pi capital R squared minus C squared over 4, because H squared over 4, excuse me. H squared over 4, because when I solve for C, I get C equals H over 2, right? So C squared is H squared over 4, all times H. And now I'm absolutely going to clean. V equals pi capital R squared little h minus H cubed over 4. And now what I'm going to do with this equation here, this is the equation that I am trying to optimize, right? This equation was just this equation after I've incorporated the particular detail about this particular cylinder, which is inscribed in a sphere with the radius capital R. Okay, I'm going to take the derivative here, v prime, v prime or dv by dh, not capital R we treat as a constant. So v prime here is going to equal, what's the derivative of this term right here? Yes, it's just the constant. Minus 3h squared over 4. And we're going to set this equal to 0 to solve for first derivative critical points. What am I solving for? I am solving for h. So let's see, let's just be really careful. Okay, and I'm going to get 4 pi capital R squared over 3 equals little h squared. H is the square root of 4 pi capital R squared all over 3. Okay, so if the height of the cylinder is this, we have a critical point. Most people will forget that they haven't shown, though, that this critical point when h equals this, v is a max, right? That's what we want. V is a max. Now let me ask you this question. If you had the choice to do the first derivative test for extrema or the second derivative test for extrema, what would you pick? I would absolutely pick the second derivative test for extrema. How on earth are we going to plug in values left and right of this on a first derivative number line, right? So come with me here. Let's take v double prime. V double equals, this here is just a constant, it's 0. The derivative of this term is going to be negative 6 h over 4. And you'll notice that in this problem, the h is the height of a cylinder, so h is always positive. So the second derivative is always negative, which means, right, you have a point here, h, where the point of horizontal tangency, and at that point, the curve v is concave down. So we know that v is max at h equals square root of 4 pi capital R squared over 3 by second derivative test for extrema. And then I'm going to go back and make sure that I answered all the questions, or the question appropriately. Let's see. Did it say, oh, find the dimensions? Okay, well, I found h. I need to know what r is. Let's see. What's the relationship between h and r? H and r, h and r. H and r right here. So h is that. H is this. That means r squared plus c squared equals capital R squared. Okay, so if r squared plus c squared equals capital R squared, then the radius is going to be the square root of capital R squared minus c squared. And c is just half of h. So when r is the square root of capital R squared minus h over 2, all of that squared, or r equals square root of capital R squared minus, what's h? H is right here. Oh my gosh. Yuck. 4 pi capital R squared all over 3 all over 4. Done. See, do you see how I squared it, Paige? See, this is squared. So when I plugged this h in for h here, it squared the square root, and the square, you still square the 2. And that is it. I have just found the dimensions. If the height of the cylinder is this, and the radius of the cylinder is this, and again, this is a number because r is just a constant and this is just a number, we have shown that the volume will be maximized by the second derivative test for extrema. All right, here's your test question. This one, let's take a look what you did. The path of a particle is defined parametrically by the equations this and this, where t is the time elapsed in seconds. Find expressions for dy dx. Okay, great. So here's what you did wrong. D squared y by dx squared. Parametrically, this is what it is. D squared y by dx squared in the world of parametrically defined curves. It is going to be the derivative with respect to t of the dy dx you found, all divided by dx by dt. So what that means is the second d squared y by dx squared is going to equal d by dt of this right here, right? 2t over sine t, all divided by dx dt. And dx dt is going to equal sine t. Okay, you can go back. There's a screencast where I talked about why this is. I think right now, since you're studying for the exam, I'm not sure you really care what the derivation is. You just want to know how to do it. So here it is. But I do at some point, you know, now over the summer, I don't know, maybe that's just me being crazy. Just go back and look through why that is the case. Now, we obviously can't leave it like this. You have to actually take the derivative with respect to time of this. That requires the quotient rule. So 2 sine t minus 2t times cos t, all divided by sine squared t. This right here is just the derivative of this, right? All over sine t. Okay, so this here is your d squared y by dx squared. All right. Part B, in words, describe the motion of the particle at time t equals 2. in a positive direction at an increasing rate. What you could have just done, and what I was just looking for here, and perhaps I should have been more specific. That's why I kind of was very lenient when I looked at what people said, because you all said different things that were correct. But I want to know: is it moving? How is the particle moving vertically, and how is the particle moving horizontally? So if you look at dx dt, okay. So if you look at dx dt at t equals 2. And dy dt at t equals 2, you will find that dx dt at t equals 2, well, dx dt is going to be sine t, right? So dx dt equals sine t, or sine 2, and dy dt is going to be 2t, or 2 times 2 is 4. Okay, notice here that dx dt at t equals 2 equals sine 2. This is a positive number. 2 radians is in quadrant 2, where sine is positive. And dy dt at time t equals 2 is also positive. So that means horizontally, right, the change in x as a function of t, the particle is moving to the right, and vertically, at time t equals 2, the particle is moving up. So here I was just looking for the particle at this time is moving up and right, somewhere in that general direction. Okay, and I think there's a third question. What was your third question? Let me see if I can find it. Let's see. Oh, here it is. Okay, what part of that did you want me to do? Let's see. You wanted to do 3C and 4B. Okay, 3C and 4B. Let's take a look at this one. All right, so, this one. Find one approximation for the acceleration of the car in feet per second at time t equals 40. Okay, so we know acceleration is the derivative of v of t, right? Because this is the velocity function. And if I'm looking for the slope of the line tangent to v at 40, right? There were several different answers I would have accepted. Some people went and said, okay, I'm going to just take the segment from here. See that point? For some reason, I can't draw on the screen. The line segment from 35, 80 and 45, 60, and find the slope of this secant line, because I see that that is very close to what the slope of the line tangent at t equals 40 would be, right? Some other people in the class took the slope of this segment line right there and the slope of this segment line and said that it's somewhere in between the two, and then they averaged those two slopes. But I would say most people took the slope of this line right here because they saw that visually it looks like that. That looks close to the slope of that tangent line. So that's how you would do that one. And what was your other question? Let me go back and see. 3C and 4B. Okay, 3C and 4B. 4B, it says, let f be a function with f1 equals 4, such that for all points on the graph of f, the slope is given by, so this is the derivative, right, that little expression. Write the equation for the line tangent to the graph of f at x equals 1. Let's just cut that. Ready? All right, so here, let's just do this. Oh. Hang on, Paige, give me a second. I'm having some technical difficulties. All right, here we go. Let's go here and paste it. Okay, so this here is a derivative, right? That's dy dx. F of 1 equals 4. Write an equation for the line tangent to the graph of f at x equals 1. So you know the point of tan is 1, 4. It's told to you right there. And you know the slope of the tangent line is equal to dy dx, which is equal to 3x squared plus 1 all over 2y. I think maybe this wording threw you off. There's right here, the part here, the slope is given by, maybe that wording threw you off, but that means nothing different than dy dx equals that. Okay, so then the particular slope you want is dy dx at the point of tangency, 1, 4. So you're going to have 3 times 1 squared plus 1 over 2 times 4, which is, what is that? 3 plus 4 is 4 over 8, which equals a half. This is the slope. So then your equation of the tangent line is y minus 4 equals 1/2 times x minus 1. And if you are feeling like really good about things here, you could say that, you know, right, you're saying that this tangent line here is a good approximation for f of x at x values close to the point of tangency 1 comma 4. Then use your tangent line to approximate f of 1.2. Right? Okay, I think at this point you can take it from here, right? All right, so I hope that helped, Paige. Good luck tomorrow, and I don't know that I'll see you all on Thursday at all, because I think Coach Johnson is proctoring this exam. But let me know if this is helpful. I hope it was. Take care.